Okay, okay. Great. So now, not all square matrices are non-singular. We will describe the test to determine whether or not a given matrix is non-singular. Now, we have conditions of non-singularity class, and that includes the necessary condition on squareness and also the second that is linear dependence. That is the sufficient condition. Now, we also had a test of linear dependence last time, and as we can see, independence last time, but again, that is a more rigorous process. Not really rigorous, but it is just a trial and error method that will be time consuming for us. Now, today's discussion is on determinant. This is a test, again, to determine whether a given matrix is non-singular or not. Again, what is the importance of having a non-singular matrix? That would yield a solution value to your linear equation systems. Okay. Now, when you have a determinant class, it's a square matrix, and if the determinant is equal to 0, that means that it is singular, meaning you cannot get, it will not yield an inverse. If the determinant is not equal to 0, then you can go ahead and solve for the inverse. Okay. For a 1-by-1 matrix, if you get the determinant for A11, A11, you'll also get A11 there. So the determinant symbol, it preserves the sign of the element. For example, if you are getting the determinant of -8, then determinant would also be equal to -8. So that symbol there, that determinant symbol will preserve the sign of the element. Now, take note, class, that a 1-by-1 matrix is not the same as a scalar. It might, it would act as a scalar, but it is not a scalar. Okay, because you know that a scalar also has peculiarities to it. But again, if you have a 1-by-1 matrix, then you will then the symbol will preserve the sign of the element. Let's proceed to a 2-by-2. Okay, so when you will be solving for the determinant for a 2-by-2 matrix, A is non-singular if and only if A1 if and only if this is not equal to 0. Ano mangyayari pag the determinant is equal to 0? A would be a singular matrix, therefore the inverse does not exist. If A is not equal to 0, then it is non-singular. Therefore, you can proceed and solve for the inverse of that matrix. How to solve that one? You will just need to get the intersection. Okay, you get the product of A11 times A22. You get the and also minus A12 A21. So ang nangyayari, class, we are getting again the intersection. So that's A11, and we also have A12 A21. Okay. Again, quite straightforward for a 1-by-1 and a 2-by-2. Okay. Let's proceed to a determinant of a 3-by-3 matrix. Okay. Again, if you have a coefficient class or a matrix that consists of coefficients equal to this one here, again, we have A11, A12, A13, A21, A22, A23, 31, 32, and 83. Again, you'll have these coefficients. I mentioned earlier that you will need to memorize. You will need to be to learn where the locations of I and J is, because again, it would be important, especially on determining the minors and the cofactors later on. So if there is something to memorize here, memorize Aij. Okay, when we say about what A11, where is that located? This and that. What row is that? What column is that? And the same goes for the other coefficients. There are two methods, class. There are two methods in that we will be particular on for this course here. The first one would be a basic one. The second one would be called Laplace expansion. So for this one, class, all we need to do is just do first. I'll use with the ones here. So we will need to get again the product of these coefficients. That is A11, A22, A23. So let's have a guide here. Okay. We also built the and also the product of this. Okay, I'll just draw here. So that would be A12, A23, and A31. Okay, I think I'll just use the guide already. Okay, so let me just repeat. So first one is the product of this coefficient. The second one would be A12, A23, and A31. So, okay. The next one also would be this one here. What is that? Yeah. That would be A13. Well, let me use the other one. A13, A32, A21. Okay. Are we correct? So we have A13, A21, A32. Okay. So again, you can have two sides here that will guide you, especially in performing such operations, such as, for example, would we be adding them or getting the difference? Okay, so this would be the first side, the side that I first run through. There's also another side class, which this side here. Okay, so that would be okay, for a while. Okay, here. Right, so for this side, we'll get the sum of this. So that's A11, A32, A23. So here's the guide here. We also have to get the product of this A12, A21, and A33. Okay. We also would need to get the product of A13, A21, A22, and A31. So here's this one. Okay. Now let me just delete this one here. Okay. So again, you have two sides. Okay. You get the sum of the products of this side here. We also get the product of this side here. And you get the difference between the two. And that you will get the determinant. Now, in other texts as well as class, you can also get the determinant by rearranging the algebraic signs. You can also look can also perform here. Okay, so aside from that, you can also do this one here. Okay, so this part class, getting the determinant using this method, there are a lot of channels that you can get that you can might get it wrong, not because it's that difficult, but because you must pay attention to the signs, the algebraic signs that you need to perform here. So you will need to really be comfortable which side you would be working on. So again, but it's just the same as all of these processes would constitute or would give you the determinant. Okay, so in general, it would look like this. Getting the determinant would look like this. Okay, so again, I suggest that you will have two sides to work on. Okay, so you will need first to the block arrows here. You need to work that one first. Okay, that would para if may dalawang sides tayo, work on the side first. Okay, now using that method, we can get the determinant. Okay, so again, we have 259. We have 167. So 1259, 167. We also have 384. Is that correct? 259, 167, 384. Good. The other side would be 286, 149, and we have 357. Okay. So again, a lot of channels that we might get not the correct answer because again, pay attention to the signs that you're using. Okay. Okay. All right. And our determinant here is equal to -9. So again, what is the implication of getting a determinant that is not equal to 0? Since our determinant is equal to -9, then it is not equal to 0. Therefore, it is non-singular. And we can go ahead and solve for the inverse of that matrix. Okay. Pag ano mangyayari again, let's just say we're working on a different matrix and the determinant for that is equal to 0. So pag equal to 0 class, you can stop there. Okay. If it is equal to 0, if the matrix is equal to 0, you can stop there because you know that you will not get any solution for that linear equation. That is how helpful the determinant is in, again, especially if determining the matrix is non-singular or not. For the next one, we will discuss the second method for determining or solving the determinant for a 3x3. But before I go there, class, I want to make sure that all of these, the slides here are crystal clear on your end. Questions? Okay, so that's questions, raise your hand right away, because if there's no question, I'll proceed. Okay. All right, very good. So part of the second method of the solving for the determinant for a 3x3 is what we call Laplace expansion. So, all right, okay, let's first delete this one. Okay, now again, paying attention to every element here, or I mean to every coefficient, or paying attention to the subscript of the coefficient class is integral to understand better the cofactors and minors. Again, if I say A33, you know where to look for that. Okay, if I say A32, you know also to look for that. When you determine if you have or you're forgetting, if you're expanding, okay, so if you're using expanding as a method to use or to solve determinant, we will come across two words. We have minors and cofactors. Okay, so what's the importance of these two? Okay, when you have a minor class, it is just Mij. Okay, so let's first look for M11 and also let's look for M31. Okay, so in this case, going back to the coefficient, let's solve for M11 here. Okay, how do we solve for M11? We are deleting rows and columns. So let's use that one. So M11 is, we delete this one here. Okay, we delete this row. We also delete this column. Sorry, let me repeat. We delete this column and we delete this row. Okay, so M11 class would be your minor for, or the M11 would be A22, A23, A32, and A33. Okay, let's, by the way, if you are expanding, you will need to do the same process for the other coefficient. Example, if you're expanding the first column, expand M11, M21, and M31. Okay, hindi pwede na M11 yung kunin lang natin. Okay? So I'm expanding in the first column. So I already have M11. Let me also get M21. So what would be M21 here? M21, we're deleting some rows and columns here. So that would be delete this. We also have to delete this. Okay. What happens is that this one here and this one here, okay, for a while. Great. Okay. So what happens thus is that M21 will consist of a matrix that will have coefficients A12, A13, A32, and A33. Okay. Now let's put that one on the side. Use that one later. So how about M31? Okay. Again, I am completing at least 3 minors, or actually 3 minors, because I am expanding the first column. Okay. So M31 would mean delete this. Okay, let's use this one. Okay. Delete this row, delete this column as well. Okay. So that would mean that this would be, okay, this would mean that, no, here, let's use that. All right. This would mean that this is our M31. Okay. Now, is it the same here? So again, that would be A12, A13, A22, A23. So that A12, A13, A22, A23 as well. meaning class that this is after deleting rows and columns, we now have a matrix for our minors. Okay, now the next thing to do about minors is we get the determinant for that. Remember, this is our discussion on a 2x2 matrix. So M11 is again the getting determinant for the minors. That is A22, A33 minus A23 and A32. Now, for this example class, just for example's sake, we only solve for M11 and M31 here. We must also include M21 here. Okay, so let me just, okay, kasi nga kailangan natin completuhin because we are solving for the first column. We're expanding the first column. Okay, so again, we get the determinant for M11, we get also the determinant for M21, and we also did get the determinant for M31. And okay, right. Now that is the case for a minor. What's a cofactor class? So if it is a cofactor, is a minor with a specific algebraic sign. Formally class, this is what we call a cofactor. That is Cij. Okay, again, very specific to the subscript. So Cij is equal to -1 raised to the power of I plus j multiplied to the minor Mij. So Cij here would known as a factor. Now, there are two ways to remember this one. The first way, class, is to, again, memorize this one. Okay, so that is, if you're getting the cofactor for C11, take note class ha, I am using 1, 1, 2, 1, 3, 1 as our minors. Therefore, the cofactors would also be C11, C21, and C31. Okay, so in this example, we're getting the cofactor, we're getting cofactors here, C11. So C11 is equal to -1 raised to the power of 2 multiplied to the minor 11. Now, saan nanggaling yung 2 class? Pay attention to the subscript, that is 1 plus 1. 1 plus 1 is equal to 2, so the raised to the power of 2. C21, that is 2 plus 1, so that would mean raised to the power of 3 multiplied to the minor. So this is the first way to look at a cofactor. Now, there's also another way, class, without memorizing this. Okay, all you need to do is pay attention to the subscript. Again, the assumption is we are working with a positive minors. So kung positive yung minors niya, kung positive yung minors niya, that is if C11, so that is 1 plus 1, that's even. So if it's even, the resulting cofactor would be positive. Again, the assumption here, class, is that all your values for the minors are positive. So kung C21 siya, that is 2 plus 1 equal to 3, so that is odd, then you'll have negative. Okay, now let's go to this one here. Okay, now let's first pay attention to this side here. Okay, so kunyari, class, that we expanded all rows and columns. To get the determinant, it's actually not necessary for you to get all the minors, but suppose you went ahead and solve for all minors. Okay, so again, this is minors. This already includes, these are actually the determinants of the minors. Okay, so if you already have the minors, class, all the next thing to do is get the cofactors. By definition of a cofactor, you are attaching a specific algebraic sign. Okay, so in this case, how do we transform this, or how do we get the cofactors from the co-minors? Attach the sides. Okay, example, if M11, again, assuming that all our minors are positive, so if this is, again, all positive yung minors, class ha, so positive M11 plus 1 plus 1, 2, even, positive. 1 plus 2, 3, that is odd, negative, negative. Okay, 3 plus 1, 4, that's even, so even is positive, that's positive. And you do the rest. And so again, taking it in a more general sense, the sign matrix, class, from converting or transforming a minor to a cofactor would be this. Okay? Again, saan nanggaling yung signs? Odd, even, odd, even, odd, even. But again, if, say for example, class, for example, negative yung yung minor mo, what would be the sign? For example, if your M11 is a negative, what would be the sign of your C11? Let me repeat the question. If you have a minor that is a negative, let's just say M11 is negative, what would be the sign for C11?
Negative din po.
Yes, negative as well. Okay, so again, it entirely depends on what coefficients, the sign of the coefficient that you're working, but it is best to at least have an understanding plus para you will not be making this one individually or parang in detail kasi you already know what is the sign matrix. Okay. How about ano class? How about this? Let's just say M12 is negative. Okay, so the sign that is attached to your minor 12 is a negative. What will be the sign of C12?
Positive po.
Yeah, positive. Okay, so I think you know that one already. So positive, 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 negative, positive, it would be a negative. Okay, so although the assumption here that all are positive, all values for minors are positive, again, you can just easily transform them depending on the situation or depending on the signs that are attached. Now, again, this is how we're getting the cofactors. Let's have an example. So this one we've already used or we've already run through with this one with my other class, but let's just say that we have not really solved this one. Okay, so let's have a numerical example with the matrix A here constituting with elements A13, 401, 603. We need to get the determinant of A to determine if we have a non-singular or singular matrix. So first is again, we get the minors. Minors is again getting, we're deleting some rows and columns. So I am choosing here to expand in the first row. Okay, so yeah, that is first row. So M11 is again, let me just also run through this one. So M11, okay, we also have, so M11 is 01, 03. We also have, sorry, okay. M12, so M12, okay, what's happening? Okay, M12 is this. Okay, let me just, right, okay, right. M12 is, oh, okay. For what class? Okay. Let me correct myself. Again, M12 is here. Okay, so that's 4163. We have M13. Okay, M13 is 4060. Okay, the next thing to do after deleting rows and columns is you get the determinant, which is a 2 by 2 determinant for that matrix. So that is 0 times 3 minus 1 times 0 equal to 0. Do the same for M12 and M13. After getting the minors, you get the cofactors. So cofactor is just again odd, even, and again paying attention to the signs. So that's 1 plus 1. Obviously, it's a 0, so you don't have to really put yourself go down that road. So that would be 0 and 0. So which left us with 6 here. So our minor is a positive 6, but our cofactors for C12 is a negative 6. The reason kasi is 2 plus 1 is 3, so that's odd. That would mean we're multiplying it with a negative 1, so that means it's a negative 6. Okay, now how will you get a determinant? That is, determinant class is A11 plus C11. So again, use the same, if you're expanding in the first row, use the coefficients in the first row. Okay, so how do you get the determinant? That is A11. So when we see A11, that is the coefficient. So that is 8 times 0. A12 is 1 times negative 6. Yeah, let me just write to have a clearer view. Okay, so let's have A here, and let's have 8, and what is 0? We also have negative 6. Negative 6, and what is that? C12. No, A1. Okay, of 1 and negative 6. We also have A13. We have E. All right. Okay. So now, again, putting those values there. So we have our A11 is 8 times C. A12 is 1 times negative 6, or C2, C12. We also have A13, coefficient A3, A13, that is 3, and C13 is 0, which gives us the determinant equal to negative 6. We can also say, class, that this matrix here, because its determinant is not equal to 0, we can have an inverse. So that basically is it for expanding or getting the determinant using expansion. Question? Again, getting the determinant does not mean that you will only expand the first row. Just like what we did here, you can always do it first column, second column, or third column, depending on what is comfortable for you. But in my case, kasi class, I just use first row or either first column so that I can visualize. It's easy to the eyes, especially when I am looking for the minors. Question? Great. So I assume that we are all okay with going to the next one. All right. Now let's go to some properties. Okay, let's go to some properties of a 2 by 2 matrix, or let's go to some properties in general. Okay. Now there are a lot of not really a lot, but there are corollaries, or there are also other properties of determinants, but there are just 7 that I'd focus, especially that these are emphasized in Chang's and Reinhardt's book. These properties are straightforward. You can verify this one later, but I want you to familiarize, okay? The first property is that the determinant of the transpose matrix of A is the same as the determinant of A. So if this is our original matrix and this is the transpose of A, then the determinant of the two are just equal, okay? So again, class, paano ba natin makukuha yung transpose? These are just interchanging the rows and the columns, okay? And getting the determinant of the two it will yield the same determinant. Okay. The next one is, if C is obtained from B by interchanging the rows of columns of B, then the determinant of C is just equal to negative P. Okay. Let's have the third one. If a matrix has two identical rows and columns, its determinant will be 0. Now, this is very similar. This is actually the discussion on linear dependence class, that if there are two rows that are identical, just like this case here, or two columns that are identical, then your determinant will be 0. So that would mean that your equation systems are inconsistent, and it will not give the same, you will either get no solutions or will have many solutions. Okay, we're very particular here with solving unique solutions. Okay, so that is the case here. Then if you have this one, class, just by looking at the matrix, you don't really have to solve it anymore, because you know that you will not get any solution at all. or the matrix is singular. Let's have the fourth one. If one of the two rows of A is a multiple of the other row, or if one of the column of A is a multiple of the other column, then A is equal to 0. Okay, again, this is our exercise about linear independence, wherein there is a scalar that proves the argument that one vector is a multiple of the other. And so here, we will end up with a determinant that is equal to 0. Now, the fifth one, the determinant of the product of two square matrices, H and L, of the same order is the product of determinants, that is, determinant of H and there and the products of H and L. Now, what is happening here is that we have two matrices. We have H and L here, and we also have the product, which is HL, equal to this one here. If you get the determinant of this matrix, you'll end up with -2. If you get the product, if you get the determinant of this matrix as well, you'll get the determinant equal to -2. If you get the determinant of the product HL, it will give you 4, which is the product of these two determinants. Okay, again, very straightforward, easily verifiable. Let's go to the sixth one. So for the sixth one, the determinant of the identity matrix is 1. So in this case, we have a 2 by 2. The determinant is equal to 1. Okay. Now, if it's a 3 by 3 class or a 4 by 4 identity matrix, the determinant is also equal to 1. Lastly, if A has a row of zeros, then the determinant is equal to 0. So if you already have a matrix that are equal to this, so pag nakita natin that there is a row of zeros, then we know that the determinant is equal to 0. So no need to really solve for determinant, because we already have a prior understanding about the properties. Question about the properties, class? All right. Okay, so if there is no question, I'll give you an overview of solving the inverse of a 2 by 2. Okay, so let's stop sharing, and I'll share a new file. New file here. Okay, so all right. Now, what we're doing here is we're solving the inverse already. There's really no definite parang steps or process, or there's no definite steps to take on the process of getting the value of x class. But I want it to be parang procedural, para we can just follow every step, and so that it's clearer. So I propose that there are around 8 steps on solving the inverse. On getting the value of an x. So these are yung first part of the process. Okay. So again, there is no definite process or steps for this, but this is actually what works for me. Okay. So obtaining the inverse of the following 2 by 2 matrix. This is the case, class, pag siya. This is a case na limited lang siya for a 2 by 2. Kasi iba din yung characteristic, iba din yung pag 3 by 3 na siya. Okay? So, starting off for a 2 by 2, if you have a given that is equal to 1, 3, and 4, this is our original matrix A here, we will first get the determinant. Okay? Before you do anything else, before performing other operations, before doing anything at all, we will need first to get the determinant of the matrix, regardless if it's a 2 by 2 or a 3 by 3, because that is it's a go signal for you to carry on the process or the procedure. Okay. Getting the determinant would mean 2 by 2, that is 1 times 4 minus 3 times 3, that's 9. That is equal to -5. So that is not equal to 0. So we know that an inverse exists. Okay. So you can go ahead and go to the next one. These are the the steps on getting the inverse. Okay. I think there are 5 for this one. Again, not these are just my own interpretation. So the first one is to find the inverse of A. Now, class, this one is already the resulting factor for a cofactors. This is already the cofactor class. Now, I think that it would also be best para lang to shorten the time consumed for solving cofactors and minors of a 2 by 2, you can just go ahead and memorize this. Okay, memorizing this, you can just easily input without going to the minors, the cofactors of a 2 by 2. You can go ahead and memorize this. Okay, so again, this is in general form for a 2 by 2. This only applies for a 2 by 2. Okay, so that's A22 is 4, A21 is what is A21 here? We have 3. Now, pay attention that I already attached the signs kasi again, 2 plus 1, 3 odd, A plus 2, I'm sorry, 1 plus 2 is 3 odd. So I attached already the signs. Okay, so again, A22, negative A21, negative A12, A11. Okay, you can just memorize this one. Okay, now attaching the values from the original matrix, we have this matrix here. We have 4, negative 3, and 1. Okay, what is the next thing to do? Transpose. So you will need to transpose that one. So transpose means interchange the rows and the columns. Our first row would be our first column now. The second row would be our second column now. Now, in this case, class, actually nagkataon lang siya na pag binaliktad mo, it will end up with the original matrix. Remember, class, the properties that we have discussed about this, about transposes? But again, in this case, you'll end up with this matrix here. Okay, so there's no point of concern. Again, even if you interchange the rows and the columns, you'll end up with the same matrix. Okay, the next thing to do is the general form of solving for a inverse. So when solving for an inverse, class, that is always inverse is equal to 1 over the determinant multiplied to the transposed matrix. So let's pay attention to this side first. Again, solving for the inverse would mean solving equal to 1 over A. So our A here is our determinant. Okay, pay attention, plus, that this symbol here will preserve the sign of the element. So even if I say 1 over A with the symbol A here, this will not become positive 5. It will still be negative 5. Okay, so that's 1 over A. So again, this symbol is specific to the determinant alone, and this is not getting the absolute value. So that's 1 over -5 multiplied to the transpose matrix, and so we'll end up with this side here. Now what happens? 1 over 5, 1 over -5 would be a scalar. Okay, so again, what is a scalar? It is a special type, a very peculiar Ka. You will need to multiply that scalar to every element in the matrix. So that is 1 over -5 multiplied to 4, multiplied to -3, multiplied to -3 and 1. So the resulting matrix would be equal to this. Okay, again, getting the inverse would mean multiplying the transpose to 1 over the determinant. And this is our resulting matrix here. The next thing that you will need to do is, remember the discussion last time, we need to verify if that inverse really is the inverse of A, because it will yield to an identity matrix. So what happens is that this is our inverse, multiply it to the original matrix A here, which is again coming from our given, which is again the original matrix. If you multiply that one, so again, take note class that there is still conformability condition. Conformability condition states that it has the lead matrix, the column dimension of the lead matrix should be equal to the row dimension of the lag matrix. Again, why are we still why are we talking about those conformability condition, dimensional requirement? We are doing matrix multiplication. Okay. Now, multiplying these two matrices, it would be equal to the identity matrix. Okay. Now, Miss, are we done with getting the values for x here because we got an inverse? Now, remember class, as I suggested, there are around 8 steps that gives you x star. So remember, okay, let me just pull quickly class the discussion on inverse. Okay. Okay. So, all right. Now remember class, the discussion in inverse, that is in order to get the value for x, you will need to multiply the inverse with the constant. And so by doing so, you will get x star equal, you'll get x star. So you have the inverse already, which is this. The next thing to do is multiply that to the vector or the constant, and you will end up with an x star. Now that would be this, this is, oh wait, okay, 4, 5. No, this is supposed to be 5. I'll correct myself here. But anyway, the 6th and the 7th, the 6th and the 7th steps would be confirming this, multiplying the inverse to the constant. The 8th step would be the analysis part. Okay, what do we mean by that x star? So this is basically the process, the procedure that I've been talking about class. Starting off with this, we will first rewrite the system of linear equations into a matrix notation. And the next thing to do is get the inverse, which is particularly all these. And then after that is we will need to verify if that is really the inverse by multiplying it to the identity matrix, just like what we did here. And then multiply the inverse to the constant, you'll end up with the x star. And after which would be the later part of the process is to analyze what the x star mean. So that's basically it for a 2x2. So I want you to take the time class. So we still have 30 minutes left, but I want you to take time to fully understand first the case when we are obtaining for a 2x2 matrix, because later on it would be a bit quite different for a 3x3. Okay. So if you have questions about the first, for the process here, for every process here, would gladly go back rather than going forward and not really understanding the case for a 2x2. Question? Okay. All right. I might let's stop the recording.